In this next segment, we're going to dive into something a little more quantitative. We're going to talk about the strength of these bonds. Okay, so the learning objectives here are going to be explain trends in bond strengths as they go between different atoms and between single, double, and triple bonds, and actually be able to estimate reaction enthalpies just using the bond energies without any other additional information. Okay, so looking at the energetics of bond making versus bond breaking. If we talk about the energy of a bond, what we're really talking about is the energy of going from individual atoms, neutral atoms, to forming those bonds. For example, for hydrogen, we are combining two hydrogen atoms to form an H2 molecule, which has a single HH bond. So there's a lot of energy released when you do that. They're going from a high potential energy state to a low potential energy state. So significant energy is released. For bond breaking, then that's the exact opposite of that process. You need to tear them apart. So that's endothermic reaction. So the amount of energy needed to break a bond is the amount of energy released when that same bond is formed, right? Just by conservation of energy. We are converting the chemical energy, which is a form of potential energy of the electrons at different levels of Schrodinger's equation, into some other type of energy that is used by the environment to do, work or to heat up the environment. We don't really know. It'll be used for something. Okay. So let's look at some other types of other dissociation energies. So for example, here, if we break apart an ethane molecule at the carbon-carbon bond, then this is a carbon, this is carbon-carbon energy. So that is that energy right there. Let's get rid of that. So that's about 350 kilojoules per mole. And if you look at multiple covalent bonds, if you're breaking a double bond or a triple bond, those are actually significantly more energy. No, they're not exactly double the energy. A double bond is not twice the energy of a single bond. And we'll explore a little bit more why when we start looking at how atomic orbitals combine to molecular orbitals. But it's definitely significantly more energy. A triple bond, again, is not 3 times as strong as a single bond, but it's still definitely stronger than a double bond and way stronger than a single bond. So that's one trend that we generally see. A carbon double bond to oxygen, again, is significantly stronger than a carbon single bond to oxygen, down here. So that's significantly stronger. So the double bonds in general are going to be stronger than the single bonds, and the triple bonds in general are going to be stronger than the double bonds. If you look at bonds between hydrogen and carbon, that's actually a little stronger than the bond between carbon and carbon. If you look at the bonds that hydrogen has with other compounds, you generally see that as you go down the periodic table, the bonds become a little bit weaker. You're seeing you're involving electrons that are, it's easier to rip those off because we're dealing with electrons that are higher up in energy levels with the molecules further down the periodic table. So same thing with carbon. You get weaker bonds as you go up to higher elements further on the periodic table. So those are the sorts of trends you can see as you look through these. Okay, cool. So those are the general trends in bond strength. Look, particularly at trends as you go down the periodic table and trends as you increase whether it's a single, double, or triple bond.